Hello and welcome to video number 10. Today we will talk about identifying time varying parameters. Alright, so first of all we need to ask ourselves the question, what is the difference between a parameter and a state variable? Alright, so we might have several different answers to that question. Maybe one answer could be that parameters are constant, but states are evolving. Alright. But then with that notion we couldn't have something like a time varying parameter because then it wouldn't be constant. But maybe our answer would be that parameters are known and states are unknown. Alright. So if we then do parameter estimation, maybe we do that once only and then parameters are known after that. But if the parameter is kind of changing with time, okay, fine. If we know that how it changes with time, then we have no problem. But if it is both changing with time and we don't really know the value of it, then we are kind of in a problematic situation, right? A third answer to the question might be that state variables are driven by input, whereas parameters aren't. All right, so for control systems where we have a clear control input, maybe that definition would make sense, but there are of course autonomous systems with no inputs, and they also have parameters and state variables and so on, so that definition is not entirely satisfactory either. So I would like to say that if a parameter is both unknown and it's varying with time, then maybe we should really consider it part of the state, so consider it the state variable. All right. So no matter our philosophical kind of stance in this question, we can make use of state estimators to estimate anything that is varying with time. So I say here time varying unknowns. All right. So a state estimator, sometimes also called an observer, it estimates the current state of a system when it has access to past inputs and also past observations, so outputs. All right. So if we now have the state obviously is changing with time, and so is the input u. But if we now also have a parameter here that is changing with time, then we can make use of a state estimator to estimate that parameter by adding that parameter to the state. So we're kind of extending the state xe. It now consists of what we previously considered the state and this new time varying parameter, so it becomes an additional state variable. All right. So whenever we do that, we should be concerned about is this new model with the extended state, is that observable? So if you have you might have observability and identifiability problems and so on by expanding the state. But say that we don't have those problems. In that case, we have now transferred our kind of estimation problem of estimating the unknown time varying parameters to a traditional state estimation problem. All right. So now the thing to note is that if your state estimation problem was previously linear in the unknowns, so here this equation is linear in the state x. If we put any of the parameters in a into x, then that is now a nonlinear state estimation problem. All right. If you have a nonlinear system from the beginning, then of course not much changes, right? It's still a nonlinear problem, but that's something worth considering. Another interesting thing to note is that if we know the state x, maybe because we have been lucky and been able to measure the entire state, then this equation here is, at least the expression ax, is linear in a. So if we know x, we could actually make use of a state estimator to estimate a as a function of time. All right, but that's a side note. We will not do that here. All right, so as an example, we will consider the same system as in the previous video. It's a quadruple tank. Sorry for the kind of black on black here. We have 4 tanks. 2 upper tanks feed into 2 lower tanks, and we have the dynamics here. And this is a nonlinear system. The state variables h is the level in 4 different tanks. They appear in the kind of denominator under a square root here. And now to make this interesting, we say that one of these parameters. The parameter A1, it's the cross-sectional area of the outlet of the first tank. Say that that parameter changes during the simulation. And we try to estimate that. All right, so here we have a definition of the dynamics. It's the equations we just saw. And here I said that if the time is greater than 500, then we multiply this parameter by 2. So it becomes twice as large. So for this tank process here, maybe that would correspond to the little outlet was previously blocked by some debris. And at time 500, the debris is unstuck. And now we have the full cross-sectional area. All right, so that's just a simple little example. Otherwise, we have the same kind of 4 equations. So here, this dynamics is just used for simulation. We still only have 4 state variables. We haven't added any additional state variable for the parameter. So I use this to simulate. So we have some data here. I've already simulated. We have some input on the right, and we have the 4 tank levels on the left. So we see that the tank levels go up and down because the pump power goes up and down. And then at time 500 here, we see that something suddenly happens, and now the level in tank 1 suddenly starts decreasing, right? All right, so something has obviously happened here, and of course it's the outlet of tank 1 has doubled in area. All right. So in this next function here, I call it quad tank parameter estimation. I have now modified the dynamical equation so that we have our state is now 5-dimensional instead of 4. And the last equation here is just 0. So this corresponds to our additional parameter. And this says that I don't have any dynamics for the parameter. I think that it's constant. And when we then use this equation for state estimation, the state estimator assumes that there is some noise affecting the state. So this essentially means that I don't know anything about the evolution of this parameter. I just think it's driven by noise. Please estimate it for me. So here now, instead of specifying a value for A1, I grab that value out of the state vector. So the state vector is the first argument here. All right, otherwise this function is exactly the same as the one I used for simulation. Then this is in continuous time. So this is a function of the derivative as a function of the current state input and parameters. And then I call c2d.rungekutta4 here to discretize that. So now we have a discrete time dynamics. So say now that we want to perform state estimation on this extended state xe. For this I'm going to make use of an unscented Kalman filter. And the unscented Kalman filter prompts us to select specify the distribution of 2 noise sources. So one noise source W that affects the dynamics, and one noise source that affects the measurement, so measurement noise here. And the UKF says that these have to be Gaussian. All right, so we need to select 2 covariance matrices, R1 and R2. All right, so I can do that. I specify 2 covariance matrices here. The R2 covariance matrix is rather straightforward to measure from just collecting some measurement data. The other one here can be considered a tuning parameter, essentially. It captures how large of an error we believe we have in our model. All right. So I've tuned that slightly, and we see it has 4 values that are the same, and then it has the last value here, the 5th one, which corresponds to the noise that is driving the unknown parameter. All right, and I said that I've tuned that to be something a bit smaller. All right, I provide an initial condition. So these are the 4 initial tank levels I guess I have, and then the initial value for the unknown parameter. I package all of this into an unscented Kalman filter, and I call the forward trajectory here. So the forward trajectory function performs state estimation over the entire data set here, U and Y, at the same time. When you run something like this, you can do that online also. So you can do it in a streaming fashion where you get one data point after another, and you continuously update your estimate of the state and the unknown time varying parameter. But here we do everything in one batch. All right, and then I plot the solution here. So we see an estimate of the now 5-dimensional state. And for the 5th state variable here, I show in dashed lines the true value of the parameter. So it starts out at a certain value and then it doubles after half the time. And we see my initial guess for the parameter was a bit off, but the estimate of it quickly converged. And then when the parameter changed value, we had another transient, and then I converged again here. All right, so this behaves exactly the way we wanted to. This allowed us to estimate the unknown and time-varying parameter. All right. So many state estimators are motivated by a statistical model. So the Kalman filter and its friends are some of those such examples. And that also means that the state estimator includes internally a posterior estimate of the probability distribution over the state. So we can use that to plot how confident the state estimator is about its estimate. And we see here for this system we had access to measurements of the 2 first tank levels, but all the other things are not measured. And we see that the estimator is rather confident as a consequence of that, of the first 2 tank levels, because we have direct measurement of those. So our measurements are extremely informative of those 2 state variables. But the other 2 tank levels are significantly more uncertain. And this uncertain parameter, the time-varying parameter, the state estimator is incredibly uncertain about that. And that means that our measurement, the measurement we obtain of these 2 tanks is not all that informative of the uncertain parameter, but it's not completely uninformative. We don't have an infinite covariance here, right? So if we would see this covariance just grow over time, that's an indication that our measurements are not informative enough to actually allow us to estimate this parameter. So then we would have to reconsider, maybe by an additional sensor or somehow in some other way measure this parameter. But here we have a bounded and non-increasing covariance, indicating that yes, we can estimate this parameter using the data we have available. So that's nice. All right, we can see if I want to somehow make the convergence of this parameter estimate faster, I can do that. My tuning knob here is the covariance matrix for how intense the noise that is driving the parameter is. So we see if I make that covariance 10 times larger. Now when I save and update this notebook, we will see that the convergence will probably be faster here. Yeah, it becomes hard to see because now also the covariance, of course, increased the covariance of the estimate. We can see what happens if I make it significantly slower instead. All right, so now we see that we have less of the noise that was affecting this estimate. So we have a more smooth estimate of the value of the parameter. But in return, we have a slower convergence when the value of the parameter changes. So the covariance entry there is kind of our tuning knob for how much filtering do we want and how fast parameter estimate do we want. All right. So to conclude, we can make use of state estimation for a lot of different things. All right. We can obviously estimate and predict the state forward in time. We can implement something called virtual sensing. So we can not only estimate the state, we can of course estimate any function of the state also. So we can view that as kind of a virtual sensor, if you'd like. It allows us to estimate the value of parameters online, so in a streaming fashion. And that of course includes parameters that are changing with time. And sometimes we want to, we have all the data available offline, and then maybe we shouldn't use a filtering methodology. We should use a state smoother instead. Okay, so we can use all the traditional state estimators like Kalman filter, UKF, and particle filter, and so on. We can use them for smoothing also. Smoothing just means that you estimate the state at a particular point in time using also future data. Typically, state estimators otherwise operate having access to only past data. Right, we can also make use of this for things like change detection, see if something suddenly changes. So the particular example we used here could be considered a change detection, right? Something fundamentally changed in our process dynamics. This outlet area of the first tank suddenly doubled. So that's a change, and we were able to detect that. We can also use state estimators to estimate unknown inputs. So if there is something unknown that is affecting our dynamics, maybe I measure the temperature in my building here and the sun is shining in through the window. Could I estimate that? And the answer is yes, I can. And that's very commonly used in the field of control systems to estimate disturbances. All right, thank you very much.